Should be recording. Good morning, good evening, good afternoon, wherever you're watching in the world. Thanks for joining in. This is your week four, module four live session for the April Data Science Bootcamp. Week four, crazy. A couple more weeks, almost halfway done. Big ideas for this week. We'll kind of go over those. This is our introduction to databases and SQL. So I got a lot to talk about just in general about databases and SQL, and then we'll dive into some of the specifics in the class content and notes for today. As you probably saw in the class content, a lot of the week this week was split into two parts. The first, introduction to SQL, relational databases, normalization, all of that good stuff. And then starting around 4:11, starting to use databases as both a source and a destination for data engineering workloads with extract, transform, and load, and connecting databases back into Python. So we'll spend most of the hands-on portion today during doing our real world project in 4:16. But I'll spend a little bit of time kind of going over databases and some of the core content as well. I got nothing on my slides, so I'll just jump straight into some of the kind of expectations for the week. It's always good to kind of frame or ground your learning in these outcomes. I think these are given to you at the very start of the week as well. If I kind of just pop into Unit 1 here. So we got to kind of get some of our recommendations for kind of the start of the day. Database management systems. Oh, Meg, this is sending me back. Yeah, big ideas. You should be able to define what SQL is as well as database management systems. Write SQL, explore relational databases, and I would also say be able to know your degrees of normalization, and then do your CRUD, create, read, update, delete, and then have more advanced querying capabilities before connecting SQL back into Python. So a lot of outcomes for the week, but they're honestly a lot of fun. I have a whole bunch of big ideas that we can tackle about as well. Kind of wanted to go over them so you double check some of the history. I think we'll go over a little bit of the history and then we'll come back into some of my notes for week four. All right, let's get going. I also have a hard out. I have a meeting at 1:30, so we have to be done here at an hour and a half on the dot. So let's get moving, I guess. All right. So first things to note, quick history of kind of databases and kind of why they're important, why they've been around for so long. So the most important influence that a database has is providing a single source of truth. I like to kind of think about all the Excel workbooks or Google Sheets that you have that you work in. And then every time you make a change, you have to save it as a version 2, and then you send it off to whoever your stakeholders are, and then they edit it and then email it around with a version 3, and then you get version 5, and then version final. Let's see if I can find like a good meme of that for like file names. Like, yeah, this is my life for a long time. It's just like, yeah, we have press release final version. Or it's like, yeah, like these are all our the final names, I promise. Like, this has got to be the final name of the file. So this is a big problem if you're working in just like Excel workbooks, you're keeping your data in tabular file formats, being able to provide updates in a consistent source of truth. If we're all accessing different documents or different locations, different versions of the file, we're going to end up seeing different data sets, right? So being able to standardize all of those into just a single data platform can be really beneficial. So the first databases started coming out in like the 60s and 70s. They have two big names in the space here, Oracle, right? They've been around for a long time. And Oracle databases, one of the first ones to market a long time ago, 1979. And then when did SQL Server come out? I think SQL Server originally came out in the 70s as well. 1980 in the 80s. All right, there you go. But Oracle is going to first to market and Microsoft quickly followed. Big thing to note about these database and management systems, both Oracle and Microsoft SQL Server specifically, they were licensed. So that means you had to pay Oracle, you had to pay for a Microsoft license, pay for an Oracle license. to use these proprietary software for storing data and information. As the technology matured into the 90s, then start coming out with the boom of open source databases. Open source databases meant that anybody could store data in a queryable format and have that single source of truth without having to pay the exorbitant fees of your Microsofts and your Oracles. And I would also maybe push that kind of moving towards these open source databases kind of led to the rise of the dot-com boom going off in the 90s and 2000s as it was easier to create database or create websites, specifically transactional websites with transactional databases. We call that an OLTP. You're going to see a lot of acronyms in database world. So databases are they just love their acronyms. So OLTP stands for transactional processing, and typically your Oracle's SQL servers and these open source databases we'll get to, they're all going to be OLTP based. Versus we'll get into a little bit later with OLAP, which is going to be for your more big data applications. But we're not quite there yet, so I'm spoiling myself. All right, where are we? We're around in the 90s. So in the 90s, a couple of big open source databases that comes out include MySQL, MySQL. So we can get the date. I think it was in the 90s. 1995. There you go. So first version came out in 1995, and the other one is Postgres, which I'm pretty sure came out in the late 90s. The origins, oh, come on, we don't care about the 1986 version. I think, yeah, maybe 1994 when it came out of Barkley. So anyway, they are Berkeley. So either way, Postgres and MySQL, this is going to be kind of the rise in the 90s of your open source. Yeah, there you go, 1995. 1996, that's when I first kind of heard about it coming out. So late 90s, you have these open source databases. And this allows for just a much more democratization of using databases as a single source of truth, right? Anyone creating a lightweight web application can spin up a website, can spin up a database, host it all for free or for very cheap, and no longer need to start paying those enterprise licenses. So we've gone from Oracle and SQL Server to Postgres and MySQL. And then, of course, with the rise of the internet, we kind of get the explosion of kind of cloud as well as kind of more complex data types. So the next database iteration in our timeline is going to be something called a NoSQL. NoSQL database is exactly what it sounds like. It's a not SQL database. So let's kind of go back and just recap what is a normal OLTP and normal SQL database. It's going to be storing your data, and we'll talk about a little bit later, but your normalized forms. At the end of the day, these are tabular tables. They have rows and columns, and they are flat. There's no nested information. There's no nested dictionaries or anything. Everything is just in a flat format that's saved as a consistent table. NoSQL allows us to save databases or database information in a not tabular format. So this is almost like a interesting way to have a governed data lake almost, or like a use case for semi-structured data sets. So the first one you need to know, the main one you need to know is one called Mongo. Release date. Let's see. I think it originally came out in the February 2009. So yeah, in the early 2000s. So in the early 2000s, the idea here was that we want to be able to store data without having to do all the data cleaning, right? So when we talk about tabular data, if your data already comes in a structured format, it's really easy to just dump it into a relational database. But if we're getting data that is from an API, right, that does look like, oh my gosh. Sorry for which one do I do? I think it's sports. If we are getting data that is looking like, sorry, my URL is wrong. If we are getting data that is not structured, right? That is lists and dictionary and with nested information. I don't want to necessarily have to do all of that data engineering work to flatten it into a format that supports that's useful for a relational database. So instead, what Mongo and some other NoSQL technologies allow you to do, they allow you to store and dump semi-structured information without any like defined tables structures to it. So we're not forced to be in a flat row and column tabular structure. We can instead be like dictionaries. If I look at this, I'm seeing a lot of squiggly brackets, right? I'm seeing a lot of dictionary-esque format, right, in terms of how the data is stored. So this provided two good use cases. The first, instead of doing data engineering and ETL, just take my raw blobs of information and just dump them straight into a NoSQL database. And then you were able to query these databases. So then you don't even really need like a fully functional database. You can just execute queries against it and keep it as is. A common use case I saw back in the day was using kind of Mongo as a data lake. So you get your JSON API responses, you dump them in a Mongo, and then when you need to maybe materialize it within your larger data estate, then you're able to write like an ETL pipeline to bring it over into SQL Server or Postgres or something. But at the end of the day, like that seems like a very expensive use case for Mongo. Other use cases I have for NoSQL is mostly on the mobile side. If I'm generate or like app dev stuff, if I am like sending information back and forth between my app and the server in JSON anyway, then you may as well just keep the database layer as JSON, especially if it's not needed for analytic workloads or anything that could potentially be used for OLAP downstream. So lightweight, small applications I also see fine just running on NoSQL databases. Now there are multiple flavors of NoSQL. What I'm showing here is like a key value oriented pair of NoSQL. You'll also, in addition to Mongo, other ones you see in the space are going to be DynamoDB, which is Amazon's native key value pair unstructured database. So you'll see DynamoDB and Mongo both used pretty hand in hand here. And you'll see like it's mostly used for like app dev development work. Besides these kind of key value pairs for NoSQL, you may have also heard of something called a graph database. Graph databases are also NoSQL, but instead of storing just like unstructured, semi-structured data, graph databases store relationships. Ooh, so it's pretty cool. Basically, anything that social network is going to be a graph. Basically, you have like your graph of who's friends with who and kind of where they're at and how they like intersect and things like that. So I love graphs. I think they're really, really interesting. And the mathematics behind kind of graph traversion is also really interesting. But graph databases are out of scope for this class. I will leave you with one name though, which is Neo4j. Neo4j is kind of the go-to graph database solution right now. And if you love Amazon, the Amazon version is called Neptune, which is like their graph little database thing, which is pretty cool. And whoa, look, that's running in a Jupyter notebook. How fun. So anyway, that's the rise of NoSQL. So it's like the two, we're bringing it back to our timeline. We're in like the 2000s, right? The growth of the internet, the growth of applications, the growth of semi-structured data. We need places to put it, so we need NoSQL databases to supplement our SQL estate. There's not very many, I don't think, organizations that only did NoSQL. NoSQL typically supplemented the main SQL database estate. So kind of interesting. And then all the cool stuff, the 2010s, the kind of rise of cloud, the rise of big data. At this time, you had what was called distributed computing and distributed storage, but it was mostly stuck to on-prem. So let me kind of define what this is. I'll give you an example, and then we'll see how this reflects on the cloud. So distributed storage, the one problem that Oracle, SQL Server, Postgres, Mongo, MySQL, all of these databases we've talked so far, the problem with them is that they have to be installed on a computer, on one computer. So if I had in my Oracle box, my SQL Server box, it's literally going to be like a rack. It's going to be like literally one computer that's just been jacked with memory, and we've installed SQL Server onto it, right? And so typically, as these databases get bigger, we have to do vertical scaling. So vertical scaling is an important concept to understand. Vertical scaling is when we just add more memory, add more RAM, add more CPU to a single box, to a single computer. Contrast that to horizontal scaling, which is where we start adding in a more computers to do the same job or to do the same work. So we buy more computers or we buy a bigger computer. That's kind of the vertical versus horizontal scaling. So with your traditional databases, right, your database management systems, you typically had to get bigger computers, right, to get bigger databases. However, at this time, there was distributed or horizontal scaled data sets. These were all on-prem at the time. The most popular of which is called Hadoop. You don't need to know Hadoop, but it's pretty fun to say, and the mascot's really cute. But Hadoop is a distributed file system. We'll do distributed file system so we can find that. So basically what happens here is this allowed us to store data across multiple nodes of computers. And you have to know everything that's going on here, but you got like data node 1, data node 2, data node 3. Think of those as like different computers, right? Across, yeah, like different server racks or something. So what this meant was that if you got a data set that was a terabyte, no longer do you have to have a computer that can hold a terabyte in its single memory. Instead, we can distribute or partition that terabyte onto four computers. So each computer only has to hold 250 gigs. And then Hadoop was smart enough to figure out that all of these files across multiple computers are actually all the same table, right? So this is the advent of distributed file storage and distributed like data warehousing. So this is obviously a lot easier to do at giant scale. So fast forward to 2015, and you have all of the major cloud providers, your Microsoft Azure, AWS, Amazon, Google, GCS, Google Cloud, IBM, IBM Cloud, Oracle has their own cloud. And so Hadoop now, like companies aren't using it by themselves. Instead, behind the scenes, Hadoop is what's powering your favorite cloud storage, which is pretty cool. So kind of how does cloud storage work? Behind the scenes, when you upload a giant file into the cloud will distribute that across its worker nodes and worker servers. Remember, at the end of the day, every cloud it does have a data warehouse somewhere, a data center. Let me get the Iowa one. Iowa data center. This is they're crazy. So this is in the United States, but you kind of have these giant like warehouses and they're all these giant data centers and literally the only thing inside of them are servers and server racks. And due to economy of scale, it's really cheap for your Facebooks, your Amazons. Yeah, the Meta's got the new one coming in. To just roll this all out and then companies just rent cloud resources that are then tied back to the physical layer down here, which is really interesting. And there's actually led some really interesting conversations on like the Twitters and the other places of the world, because what's the biggest cost that these data centers have is their cooling, right? So I actually saw, I think Coinbase, you may not have seen, this is breaking news. Um, so I can find the tweets. Yeah, this was over the weekend. Yeah. Codebase CEO says that the Amazon data center was not cooling their computers well enough. And that's why Coinbase crashed over the weekend. But I read this, I thought it was interesting for class today. Because where does it say that? Multiple chillers failed on their cloud region in the AWS. So because they were unable to like cool the computers, everything like crashed and blew up. So anyway, where I wanted to take this conversation is just like do that some of the thought exercises of, hey, like where are people like building data centers that are cool? And you have the ones that are in like under the sea, underwater data centers. I think Microsoft did this one where they kind of tried to dump data centers underground or under the water just because it's going to be a lot cooler. It's going to be a lot cheaper to cool all of those computers if you kind of have it underground with really cold water. That's just right there. It's really interesting. Yeah, I think China's doing something too from last year. Really interesting stuff. And then the other one, of course, if you're on Twitter, you see Mr. Musk tweeting about this all the time, is actually launching your data centers into space. This actually was in the news recently. But yeah, like there's some startups that want to like do this. It's crazy. It's not crazy. They've been talking about this for like years, but it's really interesting. I don't know how feasible it actually is going to be, but again, it's really cold in space, so it should be easy to chill your data centers up in space. And if it's in space, it can like power Wi-Fi going to the moon and stuff as well. So, and it's really interesting, really interesting. So it's supposed to be cheaper as well in the long run. So I'll have to do some more research into this on my own. But I forgot how we're talking about cloud. I was like, how do we get distracted talking about data centers? But yeah, when we do stuff on the cloud, like when we go to our Hadoop and deploy a data set, it's going to be saving that to a physical layer data center somewhere. So don't forget about that physical layer. But yeah, with this idea of doing distributed storage also comes along with doing the idea of distributed compute. And there's multiple different systems for this, but Spark is a good one. Spark allows us to use multiple computers to do work across distributed data sets as well, which is kind of really interesting. And of course, this is super cheap to do at scale on the cloud. So where we're going, we've gone from all these on-prem data warehouses, from our proprietary database systems, open source database systems, and now NoSQL. But now we're moving to the cloud. So on the cloud, you could do your traditional database usage. For example, you could do like AWS RDS, which is just their basic database service. And whoa, some of our favorite friends that we've already talked about: MySQL, Postgres, SQL Server, Oracle, Mariah. You can install all of those as on a regular computer and vertically scale it up, right? But where the industry has gone is we've kind of pivoted away from this for now and gone to something that's again more analytical based, right? So your online analytical platforms, your OLAP. These are going to be your data warehouses. You'll also hear data lakehouse and data mesh. So we'll go over, they're all kind of similar flavors of the same thing. Yeah, your OLAP cube. Oh my gosh, love it. So yeah, even traditional OLTP databases are now just like a thought of as a source or a destination. But with your OLAP, your idea here is that we want to have all our big data. We want to have all of our big information that we ever want to query and have it available for big data analytics. Big data analytics requires horizontal scaling, which is why it requires distributed systems and why it requires cloud to typically do this effectively. So your first kind of distributed data warehouses are going to be your snowflakes of the world. Your Snowflake, I guess, like data warehouse. That's right. I can come up with a good architecture for it. Your Snowflakes, your BigQueries, your Redshifts of the world. These are all going to be considered your data warehouse. And what's special about Snowflake, Redshift, BigQuery is that they're installed in a horizontal scaling way, right? They'll always use more. They'll always use more compute and scale out horizontally as needed. So you see, yeah, in the query processing, you're going to have like virtual warehouses and virtual distributed nodes and distributed storage to be able to do all of that work. You also see Databricks thrown in here as well, but I'll talk about that here in kind of a second. So we've gone to the advent of cloud, the advent of distributed querying, distributed databases, and your Redshifts, BigQueries, and Snowflakes. So we're about in the mid 2010s right now. Fast forward to the end of the 2010s. So this is like literally like less than 10 years ago, maybe 7, 8 years ago. You end up with the next evolution of this concept, which is going to be the data lakehouse. So to back up, you would have, if you're operating with a Redshift, BigQuery, Snowflake as a warehouse, you typically also had a data lake involved as well. Data lake is just going to be where the cloud storage location where you're dumping raw files. So a common workflow would be dump your data into the lake, into cloud storage, pull that data into your warehouse as you need it, and then also aggregate it or push it out into a Postgres SQL server for downstream OLTP type workloads if you needed it. So this is pretty dysfunctional, having some data in a lake, some data in a warehouse, but the warehouse can't see everything in the lake, and you still have to write your own pipelines. It was very cumbersome. So the new evolution of this architecture is something known as the lake house, which was pioneered by Databricks, but has been adopted by everybody else. AWS, Azure, Snowflake, Google, they all have um, different recommended architectures for this. Like here's Google's Lakehouse architecture. But at the end of the day, kind of the idea here is you should have this governance layer that allows you to quickly connect and see and discover data that's both in your lake and for your warehouse. So how do we have everything under one roof? Manage data for your data lake, as well as the distributed querying, structured querying ability for our data warehousing needs as well. And then why Lakehouse has been so widely adopted has been because if you have all your data kind of in one place, whether it's structured, semi-structured, or unstructured, and it's all living in this warehouse slash lake consumption layer, now it's really easy to start implementing AI on top of it. It's always faster and easier to bring AI to your data instead of bringing data out to your different AIs, right? Or different MCPs and stuff. If I have just one location where everything is as my lake and my warehouse, then AI can just query things as in wherever it needs to go. So we're seeing a huge adoption of machine learning and AI workloads happening on top of a lake house. The last one that I tossed out that you may have heard is going to be a data mesh. A data mesh is just like multiple warehouses or multiple lake houses at an organization. So I used to work in professional sports. In professional sports, you kind of have two different lines of business. The first is on the team side, the player side. How do I kind of make sure that my players are going to be good? My lineup is good. I have the projected wins, projected points. My formations are going to be data driven. Then the other line of business is on the business side, I guess. So selling tickets, fan promotions, sponsorships, all that good stuff, butts and seats. So two different lines of business. So imagine a lake house for the front off for the sports team, and then a lake house or a warehouse for the business side. A data mesh just means that those two warehouses can still talk to each other. You can share data between them. They're meshed together across different lines of business, and data can be quickly swapped and shared. So, again, from my personal experience working in a professional baseball team, we had our own models that would predict the probability that my team would win. And we found out that the business side was doing the same thing because if we were more likely to win, it meant more people would stay and buy more beer and hot dogs. And so I was like, all right, why don't we just use one model for this? Why are we like building two models that do the same thing? And mine was better. So we just used my model and it helped the business side out. So again, like look at that lines of business meshing across their data architectures. That's all that a data mesh is. And again, a data mesh to me can be multiple warehouses, can be multiple lakes, can be multiple lake houses, literally whatever you're building on the cloud, as long as it's governed and talk together. Yeah, one of my favorite t-shirts from Databricks was like, my other house is a lake house, and I was like, I wish it was, but that's also kind of a pun on the data side of a thing. Anyway, hopefully that was helpful of kind of the evolution of data architectures, as well as kind of where the future is going with some of this stuff. So I want to tie that back into what we're doing in class this week, which is understanding relational data and like data organization and data querying. So the next thing I wanted to actually go over was how do we store data in a relational database? So again, this is going to be winding us back to our OLTP layers, which are still very widely used in industry. Even if my company is using a warehouse like Snowflake or BigQuery or a lakehouse like Databricks, I'll still have a relational OLTP service somewhere happening behind the scenes. And actually, one last quick note on this before I kind of stop talking about cloud and stuff. The biggest innovation to ever happen to relational databases happened like last year. It's been the biggest change in relational databases in 30 years since like the open source Postgres came out. So the new one now is what's called serverless Postgres, which is awesome. Very, very cool. If you remember what we talked about, is serverless Postgres stupid? That's a great question. You remember what I talked about? If I had a regular database, a SQL Server, an Oracle, a Postgres, I had to install it on a single computer and grow it vertically. That's always made a lot of people very mad because wouldn't it just be easy and nice to have a horizontally scaling or a distributed scaling relational database system? And the answer is yes, finally. Which is it came out with Neon, which is really cool. Let's see if I can find the actual Neon architecture play page. It's under the yeah, basically it allows you to save off the Postgres memory blocks to cloud storage, and then it'll spin up horizontally scaling compute nodes that are ephemeral, and all they're doing is they're reading your like Postgres blocks from the storage layer. It's a pretty clever solution. But also, I'm the least person to talk about what the heck a wall quorum is. Just note that it works and it's really cool. And so Databricks bought Neon, full disclosure, and I work for Databricks, as you know. But I want to show that, like, well, Neon was the first to do this. It's now everywhere as well. Not IBM. Amazon does one called Aurora, which you may have seen on one of my last kind of images. Google Cloud has one called AlloyDB, which is their serverless Postgres as well that can go horizontal scaling, which is pretty cool. But yeah, interesting. Kind of this is finally happening, and they may be like, "Hey, well, how does this take out warehouses?" And the answer is like, "No, I'm still not going to be putting huge data sets, multiple terabytes or even petabytes, into an Alloy or an Aurora. They're not designed for analytical workloads. They're designed for those transaction workloads." But it does mean that if you're like Amazon.com or eBay or whatever, Alibaba, and then you're like selling products and you have millions of transactions and millions of those transactional records that are going back and forth between your websites and a database. These ephemeral Postgres solutions are really, really cool possible um, innovations to bring. Anyway, uh, so, more side notes. Let me get back to actual SQL, and then I think I may just do the data engineering one. So we'll get into some notebooks here in a sec. So when we talk about regular relational databases, one thing I've mentioned, but I haven't really dived into, is the fact that they have relationships in the name of it, right? We're not just storing data as it comes in from our vendor. We're storing data in normalized relational forms. And there's benefits and cons to this as well. So first we'll go over some of the benefits, and I want to make sure that we go over the like data normalization forms for SQL, only so I can find a good 1F to 5F gross. Usually I only do up to third normal data. Third normal form. That's usually how far I go. I'll kind of see where we can do. Oh yeah, they are 4 and 5 are bonuses. So why is normalization important? The big one is going to be reducing redundancy, right? If I have, and again, a lot of this tracks, think back to the 70s and 80s. A lot of this tracks back for 40 years. But yeah, the big problem is if I have a single computer that I'm installing SQL Server on, I need to make sure that it is memory performance, right? And we can do that by removing redundancies. When I have a single computer and a single database, it's always cheaper and smaller to store integers versus strings, right? A string can maybe take up 200 bytes, but a number is always going to be like 1 byte or 4 bytes. So it's always way more memory intensive. It's always way more memory efficient to store numbers versus text strings. That's the first thing to be clear. So now if I have a table, and one of my columns is going to be like car manufacturer. And I'm going to see the same manufacturer listed over and over and over again. Ford, 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 Mercedes, Mercedes, Ferrari, 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 uh, Volvo, BMW, whatever. It's going to be inefficient to keep all those duplicate strings. Instead, if we make a lookup table, that's maybe just going to be an ID, a numeric ID, 1, 2, 3, 4, 5, and my manufacturer. One is Ferrari, two is BMW, three is Ford, four is Mercedes. Now I can store in my master table the IDs as an integer, and that should hopefully be more memory efficient than just storing the strings itself. So we can split data into smaller tables to avoid redundancy and optimize based off of integer and I guess data type efficiencies. It also allows us to have strong controls for data integrity. You may have heard this in the lecture notes of primary keys versus foreign keys. We only want to insert a new car if the car manufacturer already exists in our lookup table. So the first ones you need to know are the only ones you need to know here are going to be your first, second, and third normalization for or normal forms. So your first normal form is going to start breaking things out, making sure everything is flat. We only have a unique value for per cell. So we have a flat tabular table, no nested content, no nested dictionaries or nested lists. Second, we're going to be removing those partial dependencies. And finally, we're going to be removing those transitive dependencies. Think about this as like primary keys and foreign keys. So let's see if we can get an example here. So here's a data set that violates the first normal form. You're going to notice that the borrowed by column is a list, right? We have three people and two elements right here. So for first normal form, we're going to flatten this table and we're going to end up with two tables. We're going to have a table for just my books and a table for who's borrowing the books. And notice that we're keeping the borrower ID as an integer here. So we end up with two tables that look like this, table one and then table two. And notice that we're foreign keying on book ID, which is cheaper to store as a number, then it would be cheaper to store this whole string, Harry Potter and the Sorcerer's Stone, over and over again. Again, just to reiterate this, if I had to kill a mockingbird for each of my borrowers, the string phrase to kill a mockingbird would be replicated once, twice, three times. And that's going to be what, like 20 characters? So 20 times 3, that's 60 characters, 60 bits used to store that information. But by using an ID as a composite lookup, we're only using 3 bits of information here. So you're saving a lot on memory by doing that. And again, think about how that scales out as your data sets get bigger. The next one is going to be kind of your second normal form. This is where we're going to start attaching and these relationships between your primary and your foreign keys. In this case, we're going to be defining a many-to-many relationship so that we have a junction table. That's what this table is called, that joins both what book was borrowed and who borrowed it and when the borrowing occurred. So I end up now with 3 tables, one for my book information, one for my borrower information, and then a junction table for when the books are borrowed, right? So the thing that says that the violation is that we're always going to have some repetition here because we can only join to one borrower. So we need to introduce a new table to get away with that. This last one here basically says, hey, there's some other solutions we can have here to remove again duplicative information. So they're moving like the due dates column out, right? And some other hidden dependencies and things. Like I would also say here, your genre should probably be its own lookup table as well. For third normal form, that's going to be a transitive dependency. We have fantasy showing up twice. That's inefficient. We should just have the genre ID as an integer be listed here, right, to remove those redundancies. And if all of this seems really kind of crazy, It is. But a lot of it is just how databases were in the 80s and 90s. So let me see if I can actually find a ERD, what this ends up looking like. So when you do this correctly, you usually end up with this is called data modeling, where we're modeling our database and its dependencies off of those relationships defined through the normal forms. I want to like a basic ERD. I guess that's fine. Oh, maybe I want the what's the movie one called? I already forgot.
I posted a really simple one in the discussion earlier
Gotcha. I don't
today.
have it up though. We'll just use Pagilla if it opens for me. Yeah, there we go. So if all goes well, you end up with a pretty convoluted database that could look something like this. So this is what I call like the movie database, and I'll post into the chat as well. But you can see we have a table with all my movies, but then it's been got all of these dependencies out. So you have film category, so that could be like the genre. So you have the category ID, that's the genre name. And then of course a movie can be part of multiple genres. So we have a junction table that's one row per, it's a unique film genre. So, like, I don't know, The Avengers, that could be an action movie and a fantasy movie and a sci-fi movie. So that would have like three rows for that film genre junction here. And then same thing, you got the actors. So this is a unique table of all my actors that ever exist. One row per actor. And now you have actors and actors go in film. So we have another junction table, which is going to be a unique mapping of every unique actor in a film, right? So one row per actor film. Notice everything is normalized, right? It's one row per thing. Every row is flat in terms of its content. There's no nested lists or anything. And we are memory efficient by breaking out all of our repetitive strings into its own like identifier, which is kind of crazy. And then yeah, you eventually map this back to the rentals. So imagine you're a Netflix, a Blockbuster, you're renting movies. I need to know what is my movie store? What movies do I have in inventory? Of course, I could have more than one film in inventory. So this is actually a junction table. I have three copies of Titanic. So I need one row per inventory ID per copy. And then people can rent out those movies. And of course, you could rent two of the same movie, and everything else kind of just blows up huge from there. So this is kind of your like gearing towards your OLTP, your relational database architecture. So that's where we spend a majority of kind of the week is going on taking data, breaking it down into its normalized forms, loading it up into tables. And then when we're querying this type of a database, we have to start joining a lot of these tables back together. So that's where you're going to see a lot of those different types of joins, those upserts, and then those CRUD operations, those create, read, update, delete. How do we start creating, reading, updating, and deleting information from a database that looks like this? Cool. I think that's all I wanted to go over in terms of some of those foundational things. Yeah, because then you start going over your basic SQL queries, which is how we start extracting data from those types of databases. Yeah, they're like not too complicated. Let me just go through a couple of the other ones here. Yeah, so as you start going over some of these other videos, everything I just went over about the entity relationship model, that's the same thing, right? We're defining how a database should be broken down based off of its normalization, its data types, primary keys, and reducing redundancies. Yeah, there's some good discussions on this. I preceded a couple of the forums, which we can get into a little bit later. And then you should hopefully already see kind of what the queries look like. So yeah, again, a lot of acronyms in database land. Already mentioned CRUD a lot. The other one that you'll see is DDL, your data definition. That's just going to be how is the table structured or configured. DML is like data manipulation language. So that's going to be like your CRUD operations as well. If you want to play around, remember all enrichment activities are optional. If you want to play around with spinning up a database, again, it's the exact same thing as if you're doing like AWS RDS. So you'll be using the IBM cloud with your free account. It's provided through the bootcamp, and you can spin up your own single node deployed cloud database, right? So this would be just like installing SQL Server onto your laptop. We're going to be installing, I think it's Postgres onto a single just virtual machine on IBM's cloud with DB2. Next couple media sets is went into advanced querying. So this one's looking at irregular expressions. How do we look for substrings and things like that, as well as adding in additional clauses to our queries? How do we do order by? How do we do where filters? How do we do group bys and having filters as well? And then start using some of the built-in functions. So this would be like your mean, median, max, average, all of those kind of built-in arithmetic functions, and doing subqueries with joins. Uh, Personally, I think subqueries are kind of dumb. They only have like, to me, they only have purpose in pretty specific situations. Again, this is a decent example, but most of the time when I was working through this week, I would have used a join instead of a subquery. Um, but yeah, usually either one type works, but I think joins are easier to read. And I think that's mostly here. Subqueries and nested selects. Yeah, gross. Cool. Let's see. What was the last thing on here? Oh yeah, the cheat sheet. The cheat sheet's pretty good. I would definitely reference it. It's in my GitHub too if you need it. Again, it kind of includes a lot of basic functions that are pre-built for you in SQL, which is pretty nice. The last thing here before we jump into some of our hands-on activities. Um, once we're one quick thing I want to last thing on databases, and then we'll jump into databases with Python. So last thing on databases, one thing to keep in mind is that SQL as a language is important. So in my notes, this is important. SQL as a language has different flavors. So all of the databases we've talked about today, Oracle, SQL Server, Postgres, MySQL, Mariah, Mongo, Databricks, BigQuery, Snowflake, Redshift, every single one of those is going to have a slightly different syntax for SQL. And you're like, what? Yeah, it's super dumb. All these database engines, they have like different optimizations. So for example, one that I haven't touched on yet, but one that we're going to be working extensively in our Python notebooks is a database format known as SQLite. SQLite is basically like a lightweight version of a database that allows you to save a database off as a file, which is pretty cool. It can be really slow and doesn't scale very well, but it's cool to have a database as just a file that you can email around or attach to a mobile app, for example. That's where we see them used a lot. But for example, a SQLite database doesn't have a datetime type. It doesn't know that a date exists as a date type. So you have to use a lot of funky kind of string manipulation
Oh, it
to get
it,
it
it
good
does
data.
have a datetime format. It does have datetime type.
Mm.
I've used it. In fact, I just used it recently.
I think it's saved in as text.
No, no,
It's
it
like
is a
a weird
datetime.
thing.
Datetime.
Yeah.
It might internally do it as text, but you do have a type for that.
Yeah, that's stored as yeah, it's gonna be stored as like a yeah, it doesn't have the storage class for dates. Instead it uses the functions, which again parses it out of strings
Maybe.
and
I just know those
uh,
I was using it, so
yeah, so it shouldn't have a specific. If you create the table, I don't think you can create a table with date type, but maybe you can now. But yeah, like other things too is like some of them, like MySQL would be like if I want only the top 10, I would have to be like I would be using top versus limit, like in SQL flavors. So some of them allow you to do yeah, like SQL Server allows you to do select top 10. But other ones you have to do select star limit 10. So it's kind of funky. So like SQL Server makes you do things that other databases don't. So yeah, long story short that I
oh,
want to get
oh, you're
across.
right. Oh, sorry. You're right. Now I'm looking at what I was doing. It does do as text, but has conversion stuff in it.
Yeah, the datetime conversion stuff in the function. But
Yeah.
yeah, long story short here, depending on your database type, you'll have a different flavor of syntax. And if you really bonus quiz points, the Microsoft flavor is called T-SQL or Transact SQL. So some people will be calling like, hey, do you know T-SQL? And that's mostly like, hey, do you know how to write a SQL query in SQL Server at the end of the day? But yeah, all the other ones, you're like Postgres SQL, right? Versus Databricks SQL. DBC, we call it a Databricks, it's called like DB SQL. That's like a whole thing. So just in terms of like syntax. So yeah, a lot of weird syntax stuff, right? But yeah, you can say like limit 10, casting is a little bit different. Creating procedures and stuff is a little bit different. So a lot of different syntax things you got to keep in mind. With that being said, though, don't worry about memorizing syntax. Memorize big ideas about why databases are needed, the different history and evolution of databases, how databases fit into a modern data ecosystem, how you can have NoSQL, data warehouses, OLTP, data lakes, all living as like one architecture together. So the next few activities here, we're going to be opening up notebooks in our Jupyter notebooks and writing queries against them as well. So you can see here that we're going to be basically connecting to the database, writing SQL queries, and then using those results in our um, exploratory data analysis, creating visualizations, all that good stuff. All right, I think I'm gonna pivot into the activity that I wanted to do today, which is gonna be 416. So yeah, we don't need to go over some of these basic notebooks and things. Well, then 415 is gonna be another enrichment activity, and then 416 is the real one. All right, so let me open this guy up. In this activity, we're going to be working with three Chicago data sets. We're going to have three tables, and we're going to be practicing writing a bunch of SQL queries to see how we do here. While that's loading up, I did run all these other notebooks in my week 4. Yeah, good. Whew. I was like, I should have week 4 already up here. But yeah, for example, like the 411 ones, I'm just like writing SQL. So you'll see that's like a basic one here. This is like our hello world. We're going to be loading in SQL, connecting to a SQLite database. You can see how we created the database with the syntax. We have 4 columns that are 3 of them are text, one of them's an integer, and then we should be able to. Oh, I was trying to run this locally. I don't think I was having some trouble with it. So that one didn't work for me locally, but some of those other ones should have. Yeah, there we go. So you can write the query and then you'll be able to bring it back. And of course, this will implement really well with pandas. So for example, here we have my query, select star from the instructor table, and we're able to read it natively into a pandas data frame, which is really cool. And then 413, I think, was also pretty interesting. This is like a good warm up for 416. It's going to be similar Chicago tables that we're going to be using in the final activity for the week. Load in the create the database table. So here we go, and then we can select some of the queries here. So here we're just writing some more advanced queries. Notice we are using a where clause. We can do one line as well as multi-line queries. And notice what else we can do. Oh yeah, there we go. Using a subquery here. So that's fine. And then yeah, order by, limits. It's a bunch of good stuff. All right, so let's jump into our notebook here, which should be good to go. Cool. We're connected to the query. This is going to be our 416. And our goal for this project in this notebook, we're going to be interacting with 3 tables. We're going to be writing a bunch of queries and then calling it a project. How do I get my clear output of all cells? All right. So mine's probably already been filled out. So but definitely feel free to follow along as you want to here. Notice that this pretty table default thing, I just set that because for the IBM user interface, it kind of loads some of the files a little, or some of the results a little bit funky if you don't. Okay, so we're loading in pandas. We're loading in kind of our CSV and SQLite helpers. And here's what we're going to do. We're going to connect to this database. So this should just work. And if this database didn't already exist over here on the left, it would have created it for me. We're loading in this magic. All this magic module thing is it allows us to write SQL queries in the notebook and have the notebook see that it is a SQL query. Otherwise, right, this notebook thinks we're just writing Python code. So it's going to assume my syntax is Python. So this allows us to force the notebook to view it as a SQL query when we get down here. More smarter notebooks out there, for example, SageMaker or Databricks notebooks, they can automatically infer or pivot kind of the execution type based on the language. All right, first what we're going to do here is create our three tables. So table number one, we're just creating, we're doing our, I guess, our extract and load. We're extracting from this cloud location on IBM, and then we're saving the data off directly to my database. Notice this connection here. This con is my database. So we're creating the census data table, Chicago Public Schools table, and Chicago crime data. And if you're like, wait, Booth, why, if you're just reading the data in pandas anyway, then writing it to the table, but then you're querying it back into pandas. I know, hush. Just think about this as like a separate ETL pipeline. We're going off to the world, getting our data set, extracting it, and then we're going to, and then we're going to uh, load it back into the database. And then in a separate workload, maybe it's a different person, we're going to go query our data estate for information as an analyst or data scientist. All right, last thing we're going to do here, next thing we're going to do before we get into the problems, we're going to define this database as our primary SQL connection. So whenever I run this command now, which is a multi-line SQL query, the extension knows to execute this query against this database. And this database could be a full cloud database. You could have a full JDBC URL, but in our case here, we're just querying the flat file. All right, so first what I'm going to do here, I'm just doing a quick limit one, just so I get a breakdown of the rows that exist in my database. So in this case, we have all of these different columns, and here's an example of what a row looks like. So we have a theft from a building of a small retail store at this address. And we have the latitude, longitude, and year location. Cool. So to find the total number of crimes, I'm just going to count ID. That's going to give us the unique count of ID here. ID should be unique by definition. Know that another way you could do this is to just do select star or select count of star. My problem with this is that it's I would typically only look at the columns that matter just to make the query more optimized and use a column that's guaranteed to be unique. So in this case, the primary key. List community area names with a per capita income less than 11,000. For this one, we'll be using the census data table. Here's what the columns look like. So here we need the community area name, the community area number, and we need the the per capita income to be less than 11,000. So that's what my query is. And it's nice to be able to speak the query into existence. Select these columns from the table where my income is less than 11,000. And then just for cleanliness, I ordered it by income ascending. So we can see the community area with the lowest per capita income is Riverdale, followed by South Lawndale, then Fuller Park. This is all in Chicago, so I actually know Fuller Park. So kind of interesting. Anyway, let's keep going. List all case numbers for crimes involving minors. In this case here, I ended up using minor as a string query. So this like keyword basically allows us to match text where this exists as a substring. So again, definitely work through that notebook if this is new to you. But essentially here we want all rows where the description contains the word minor anywhere in the string. And we have two matches. Note that we have minor appearing in the description twice. Sell give liquor to a minor and illegal consumption of alcohol by a minor in an alley. At least it was 20 years ago. Next one, I'm gonna keep it the morbid, morbid cases here. List all kidnapping crimes involving a child. So same idea. I want primary type to match the substring kidnap and description to match the substring child. And we end up with right here, we have a child abduction happening on a street. I didn't bring back the block, but I guess we could. So West Van Buren. Next, list all the kind of crimes that were recorded at a school. Again, we're still doing our string filtering here. So definitely review the string filtering notebooks before you work on this one. And yeah, we can see cannabis, heroin, golly, public peace violations. Oh my God, America. Anyway, a lot of dramatic crimes happening at these schools. And then if we wanted to, maybe we wanted to answer the question more specifically. This is matching like each individual rows. Depending on how you understood the question, it could also just be what are the unique types of crimes that occur at schools, in which case that's what this query does. Select distinct, that also means unique. Select unique rows, unique primary and unique description combinations where the location happened at a school. So these are unique unique crimes. We have assault, battery, criminal damage, narcotics, and public peace violation. Next up, list the type of schools. So we do a select star limit 1 to look at the first row, and we want to do a group by to get the average safety scores. So we're going to select the type of school from this column right here. One thing to highlight, I had to use backticks to select the column because this is a disgusting column name. It's got commas, it's got spaces, it's got a lot of bad foreign characters for our code. So I have to just escape all of those foreign characters with backticks. A better column name for your database would be something like this, any of these other ones. Replace your spaces with underscores and try and remove all foreign characters. So let's actually do our group by, and we can see here that our high schools are actually the safest on average, which is interesting. Same things here. We want to look and do some more aggregations, some group bys. We want the 5 community areas with the highest percent of households below the poverty line. Couple different ways to do it. I think this is the answer, but this is how I just did it, which is a lot easier. Basically, just look for yeah, just order by the percent of households below the poverty line. I didn't really get why I did a group by max. Essentially, what we're doing here is that this table is already guaranteed to be unique at one row per number and name. So if we're only going to have one row for a community area number and name anyway, you don't need to group by it because you're just group the average of one row is just still that same value. So that's what this is doing here. The max of one row is the same as that one row's value anyway, right? So you don't have to do a group by if it's globally unique. I don't know. So that's just why I did it this way. It was a little bit simpler. And we can also do this directly with pandas. This is how I usually write SQL queries in my Jupyter notebooks. What I'm doing here is I'm writing the query off as its own string, and then pandas can read a SQL query. So I'm executing this query against my database connection and natively reading the results back into pandas. Next up, which community area is the most crime prone? Display the community area only. So again, same thing here. We probably didn't need to do a group by. Um, oh, I guess we are because we're doing a join. So here we go. We do our first join here. We're joining the crime data to the census data, and we're joining on that community area number. And so we can see here that the community area number of 25 in Austin, that had 43 crimes in my crime table. So that's a lot. Humboldt Park, I also used to live pretty close to there back in the day. They had 22 crimes, which is interesting. All right, almost done here. For this one, this is a good use of a subquery because it's just a small, quick thing. We want to get the max hardship index from census data. Sure, we could just run that by itself and hard code in that value, but by doing a quick subquery here, we can have this be dynamic. If the hardship index ever goes to 99, our new query will automatically pick that up. We don't have any hard coded values. Last one here. Use a subquery to determine the community area name with the most number of crimes. I did not use a subquery. I used a join. I'll leave it as an exercise for the reader to refactor to use a subquery. But to me, this is the type of question that a join makes a lot more sense. We need to join my crime data to my census data. And then from there, we're going to group by the area name and number, and we're going to count all the crimes. So the community area with the most crimes, like I showed all the way up here, is Austin. So basically the exact same query as number 8. One quick thing to note, when I do joins, I try and have my smaller table be the target of the join. So the crime data is one row per area and crime, while the census data is one row per area. So the crime data is always going to be bigger than the census data. So I want my crime data on the left and then joining the census data onto it. But there's no real right or wrong with that as well. Just make sure you learn your joins. They are important, and I'll share my meme of the guy's hair because I think I've been teaching this for 8 years now, and I still use this guy as my go-to. So let me open this image up. I guess that'll work. Yeah, left join. So we have the mustache and the beard. Right join, the beard and the mustache. Inner join, we only keep what's connected in both, just the mustache. And the outer join, we bring everything back, which is kind of fun. So just make sure you know your joins and you should be good to go. The last thing I'm going to do here, and actually, I think that's it. I want to do the quiz though before we're done, but I'll download that. Cool. Let's go over real quick the quiz here, and then yeah, don't worry, I'll provide all this as resources after class. Yeah, I'd rather use the Geeks for Geeks version. Yeah, I probably should throw that one in. Cool. Let's go over the quiz and then hop out of here because I got a hard out in 10, 15 minutes. Hopefully the quiz isn't too bad. Update instructor set last name equals Brewster, where last name equals Smith. So what does this do? This will change the last name of the instructor named Brewster to Smith. No, we're gonna find the rows with Smith and we're gonna change that to Brewster. So the answer is gonna be C. Change the last names of people with Smith to Brewster. What would occur if you execute a delete from on a table without a where clause? It'll delete everything, right? The command would delete all rows, but it would still leave the table structure intact, or this table schema intact. What was the expected result? Select count distinct from instructor, the number of unique first name entries in the instructor table. Which of the following statements is correct? Only SQL can be used to query data. A database is a logically coherent collection of data with some meaning. Data can only be added and queried, but not modified. D is incorrect. A is incorrect. C is incorrect. I'm pretty sure it's B. The create table statement is a DDL. It's a data descriptive language, whatever it is. Which command is used to remove a table from the database? Drop table. Truncate deletes all rows. Alter changes something. Create creates something. In SQL, which the following would be the correct way to sort a result set in descending order? We want to order by something descending. Doesn't A and B both work here, technically? Select ID from table, order by ID descending. I
Yeah,
think
they
the other way
they
is,
both do. They want B, but yeah, they both work.
yeah,
I
I
think
think
we raised that up before
do we?
last
Yeah,
cohort. Yeah.
I think it's going off of result set, which is going to be more rows than just ID or more columns than
Well,
just
that's
ID.
more
So it wants,
column. Yeah. So the data
yeah,
set that could be a data set with just one column too. So
yeah, it's dumb. So I would go B here, even though A is technically correct as well.
well, A would be kind of silly and redundant though. I mean, you're just going to get the number of IDs and in order. Well, it's going to be one,
B would
two,
be
three,
the
four,
best
five.
answer. Yeah.
Yeah.
What's the role of the having clause in MySQL? Having clauses are a filter where clause that execute after a group by. So it, let me see what we do here. Checks whether the data record to meet the condition or not. Restrict the result set for a query using group bys. I think it's B.
Mm-hmm.
Organize the result set or acts as an alternative to where. So technically it does act as an alternative to where, but not, you can't just use it without a group by. And technically A as well, it does check whether a result set meets the condition or not. But I think because of its use of data records here, it doesn't check raw data. It checks the results of a query using a group by. So I think the answer is B is the
It's
best
also
answer.
because where does not work with group by,
Yeah.
but otherwise having does not work otherwise with queries. So
Yeah. So
I
when it
always make the mistake of doing where in a in a group
So
by.
just for
Always a
completeness
mistake.
here, I can add a having clause after my group by, so I can now filter off of number of crimes. Having number of crimes be greater than 20. So this should only bring back, if all goes well, Englewood, Humboldt Park, and Austin. Yeah, which it does. So notice that we are filtering after the group by. So technically you can have both where and having in the same query, the more you know. Cool. Last couple here. Which of the choices best describe the function of the following SQL query? Select star from employees, order by employee name, limit 5. So we are going to be retrieve all the columns, check, or retrieving all columns of the top 5 rows, sorted reverse alphabetically. No, this is going to be ordering alphabetically. That'll be by A. Retrieves the top 5 employee names ordered alphabetically. Retrieve the entire content of the table sorted alphabetically based on employee names. So the answer is D here. That's the best answer. 5 is not right because we don't just care about the top 5 rows. Same with B. B is also not reverse alphabetically. 5 isn't right because we bring back more than just employee names. D is right. We bring back the entire table sorted alphabetically. Which two of the following can be stated as uses of the cell magic? Coding in languages other than Python, that could definitely be a thing. Timing is also a thing. You can time different cells with magic commands. Converting default programming languages, I don't know if that's a thing or not. Loading a SQL database to a Jupyter notebook, I guess so. If we say
Look
AB, I
back
don't
at
know what the answer is.
look back at 9. Look back at 9.
Oh God,
D is wrong. Why is it
is it?
wrong? Yeah,
Loki,
because you're
is that?
limiting 5, so you only want the top 5.
Okay, I was thinking about where's my notebook? My notebook stopped rendering.
OD
Love me the
doesn't include the limit clause. Doesn't
Sure.
include
Thought that was like when we did I want to show you the line in the notebook.
no, it's
I'll say
just
here's what's confused. I think when we do this line in the notebook, that's when I guess that's not loading the database into Jupyter. It's establishing the connection. So yeah, I would probably just go A and B here. I think that's fair.
it's A.
Not you wouldn't say B? You can
Oh,
definitely
for
use
that,
timer.
I'm still on 9. I'm still on 9.
Oh, I'm
D
on
is
10.
wrong. D is wrong on 9.
D is wrong on 9. Oh, because we
because it
are
doesn't have a
limiting
limit.
5. Oh,
It's
I
it's
started.
A.
It's A. Retrieve all the columns with the top 5 rows. I would say to be sorted and then it's the top 5. Yeah, I guess A will work there.
A is
Fair
right. I
enough.
know because I got 100 on it.
Nice. Well, what's the answer to 10 then? Is it just A and B or is it A, B, and D?
Uh, wait. It is a weird one because it doesn't talk about it. So, but yeah, it's A and B, which doesn't make sense for anything that it described because it didn't really
Fair
give a
enough.
general idea of what the magic commands do.
Yeah. What would be the outcome of the following Python code? Um, they are connected to the database, they are reading in a CSV, and then they are writing out the CSV to a new table called employees in the database. The CSV file is saved to the database file created by the code. The CSV file is read and converted into a SQL table. That's what it is. So yeah, we're reading in the CSV and we're writing it out to a table. Last one here. How do you do a statistical analysis of data in a pandas data frame? That'll be dot describe. Info brings back metadata about the columns. Head brings back your top 10 rows. Tails bring back your bottom 5 or 10 rows.
And doesn't belong here at all.
Yeah, weird question. We'll get more into this type of work in week 5. Week 5 is our introduction to exploratory data analysis. So we're going to be doing our EDA, our pandas statistical analyses, and our visualizations on kind of just, I guess, data distributions as well. We'll wing it and see how we did. We're right on the money here. Oh, wow. 12 out of 12. Good job, us. I probably
You,
would have missed one or two if it
you
wasn't
can
for
you
Karen.
can thank me. You can thank me now for
Yeah, thanks,
that's
Karen, for
enough.
getting me a 100 on the quiz. Last thing before we wrap here, I want to make sure I cover some of my big ideas for week 4. So this is my own lecture notes for the week. So big note, big ideas from today. Data scientists don't just analyze data, especially not just from source. They both read and write to databases. So databases can be a source for engineering pipelines or data pipelines. They can also be a destination. We want to save our data, our results off to a database as well. Again, mostly it's keeping that single source of truth as a database, regardless of if you're pulling from a web scrape, you're pulling from an API, you need to save that to a single source of truth. Or if you create a machine learning model, you generate predictions, you need to save those predictions off to a single source of truth as well. The real world data lives in relational databases, which is the bridge between querying, analysis, and real world application systems. Big things to know about databases. Key in on the relationship side of things. So they're going to be tables and schemas and specific data types. You're going to have strong controls around those relationships, specifically primary keys, foreign keys, data normalization, things like that, ERD diagrams. You should know all of that as well. What is a relational model in database design? How do entities map between tables and columns and everything? And why primary keys and foreign keys matter. I would also say you should also know kind of the evolution of databases over the last 30 years, 40 years, going from the proprietary single node SQL servers, database management systems, to your open source, to NoSQL, to cloud, to distributed warehouses and lakehouse models. Big idea number 2, SQL. Yep, data definition, DDL. So your create, alter, drop, truncate. Your data manipulation. This also be your CRUD. Insert, select, update, delete. I'd also make sure you know CRUD, create, read, update, delete. That's basically kind of what DML is over here. Let's see. Querying is set-based thinking. You're not looping or iterating. We're moving things in a procedural way, typically from like declarative statements. So I always start with where am I getting the data from with my from and my joins. What columns do I want to bring back? And then any filters and things as needed. So select where, order by, group by, count distinct, your built-in functions. Queries, I would also add in joins here as well. The SQL is about describing what you want, so make sure you understand that too. Let's see. Most databases have more than one tables, multiple tables. You need to get comfortable with joins and querying across tables. We also know how to integrate with Python now using the different magic commands as well as different libraries like SQLite 3 and pandas. But this is how a real workflow goes. Take your data and pass it through back into pandas. Once we're in pandas, we can do anything we want. The real world data is messy, but your database is supposed to be clean. So you need to get comfortable operating on dirty data and then transforming that dirty data into something clean and usable. Yeah, and then finally, make sure you get comfortable this week with the big ideas of the whole workflow and integrations of the data ecosystem and the data architecture. You don't need to be memorizing T-SQL syntax, but you should know kind of the full life cycle. Get data from wherever, web scrape API, load it into a database, and then create tables, have relationships between those tables and then query that data back out into other complex like Python workflows, and then write those results back to a database, right? So make sure you understand schemas, queries, multi-table reasonings, and how everything kind of works together. So designing tables, loading data into tables, querying tables, and then visualizing or pulling results into the pandas side. Well, I think that's all that I had here. I'm trying to be literate with data architectures, not just memorizing select star and how databases work. Let me make sure I hit all of our big ideas. We defined SQL. We looked at foundational SQL statements. We looked at relational databases. We created, modified, and deleted tables, query results with advanced querying, and we did the real world data sets. So we did a lot here in an hour and a half. Hopefully, this was useful or entertaining, or you learned something along the way. I have 128, so this is good because I have a hard out here in the next minute or two. But Henson, if you have questions, feel free to come off mute or drop it in chat. Otherwise, I think that's all I got for this week. Next week, like I said, is EDA. It's kind of like week 3. It's less notebooks, but each notebook is pretty important, especially weeks 5 and 6. I guess 5 is a decent number of notebooks here, but these 5 and 6 kind of get in a rhythm, and 7 and 8 when we get into like the machine learning stuff. We're done with like high-end learning broad concepts, and now like what is a SQL, what is a Python, and now we're doing like real data science workload stuff. So yeah, next week is all EDA, week 6 is all visualization, and then week 7 and 8 is all machine learning. And then week 9 and 10 is the capstone and advanced AI topics. So it should be fun. Definitely spend the time going over the next few notebooks, the next couple weeks here. I think we're getting to the meat of the program for the next month, and then we'll close out with our capstone. Thanks for the time. Thanks for the attention. Open it up here for questions, and then we'll close the room in about a minute or so. Thanks, everyone. Cool.
I guess
I will.
that does it. Our audience is gone.
I'll stop the recording.